then the Kw is 1.0 times 10 to the minus 14. Okay, everybody remember those terms? Those are important things that you need to know. Okay. So then, when I have the hydronium ion that's greater than 10 to the minus 7, that means the hydroxide's less. That creates an acidic solution. When they're the same, both 10 to the minus 7, I have a neutral solution, just H2O. That means you have the same amount of each of these ions. And when I have more hydroxide than hydronium ion, I have a basic solution. And whatever I put in will cause that adjustment to either increase this or this based on how they interact with the water. Okay. But the Kw is always 1 times 10 to the minus 14. Okay. Okay. So, what is the concentration of the hydronium ion and hydroxide ion for a 0.25 molar solution of barium hydroxide? So what do I need to do for a problem like this? What would be the focus here? Okay, so let's start with an equation, right? So what am I doing? I'm putting this thing in what? Water. So what happens to it? The first question is this strong or weak? No, I think we did talk about strengths already, right? And with hydroxides, I have a strong base here. That means in water, it's going to dissociate completely into Ba2 plus ion and 2 hydroxide ions. That 2 is really important there, right? I'm balancing this out. Because if I have 1 barium per barium hydroxide, I also have 2 hydroxides per 1 barium hydroxide. Okay, something that we manipulated and learned in Chem 101 in terms of stoichiometry. Now, that means I have 0.25 mol. Let me go back. First, I want to make this very clear. This is strong, which means I only have an arrow going one direction. Right. That's really, really important in this evaluation, and will be a follow-up for something we're going to do in, say, 10, 20, 30 slides from now. Okay? If it's strong, that's one arrow. There's no equilibrium form, presumably. Yeah. Okay. That means that I start with 0.25 molar of this. I have 0.25 molar of this, and 2 times 0.25 molar of this. Okay. Is that clear? Yes. Because what am I looking for here? I'm looking for these 2 concentrations. So what did I just find? I just found this concentration here. Yep. If I know that concentration, can I solve for that concentration? Yep. Kw equals what? 1.0 times 10 to the minus 14, which also equals what? The hydronium concentration times the hydroxide concentration. Okay, maybe I should have started with that slide. That goes back. Let's make sure we're aware of what I'm saying. This right here, right? So this is what we finished off with last week. So you must know this, and then this, of course, equals, as I said, 1 times 10 to the minus 14. Okay? So now that we know this, I can now solve for this based on the knowledge of this, which of course is just 0.5 more. So a couple important ideas when I started this problem. One is I evaluated this and saw that this was a strong base. 2, I was able to put that into some kind of an equation to indicate the ratio of things based on the stoichiometry, which are the balancing of it in terms of the coefficients. Next, I was able to identify that once I found this, I could then find this if I knew what Kw was, right, which will never change. It's always 1 times 10 to the minus 14. So then I say Kw equals this times that. I know this, I know what that equals. Can I now solve for the hydronium ion? Yeah. And of course, absolutely. Now it breaks down pretty easy, right? It's just Kw over the hydroxide ion concentration. And that gives me this. Yes. Now, the next thing I could say is, well, if I have a neutral solution, then what would my hydronium and my hydroxide concentrations be?
The square root of that?
They'd be the same, which would be what?
1.0 times 10. Yeah, 10 to the next 7.
Absolutely, times 10. So then is this right here greater than that or less than that?
That is greater.
It's greater, which means that this one has to be less than,
Yeah.
which means what kind of solution do I have? Basic, absolutely. So I can determine from this, if I have something, whichever one is above 1.0 times 10 to the minus 7, then that's the type of solution I have. If I have less than that, then that's the type of, then that's not the one I have. Right? Since the hydroxide is greater, therefore I have a basic solution. If the hydronium was greater, then I would have a acidic solution. If they're equal, neutral. And that's what the previous slide showed us. So now we're just putting it all together in the context of a problem. Okay. Oops. So what is the concentration of, so we're going to, I guess this is going to ask the same thing, except for now, the first one was a basic, was a base. Now I'm looking at an acid, HNO3. So it says, what's the concentration of the hydronium and the hydroxide? The very first thing, I look at the base, what do I say about it? Is it strong or weak?
Strong, weak.
And it's strong. How do you know it's strong? If you didn't have a chart.
Yeah, mono oxygen.
2 more oxygens per
Minus
hydrogen,
one.
2 or more.
Right.
Strong. So it's then if I put this in water, what equation do I get? Okay. Of course, I could take out the H2O here and the H2O there, and I could just say HNO3 with an arrow, H plus NO3 minus.
H plus, right.
Either are appropriate. Okay, does everybody get that? Should I write that out? I hear, yeah, let me write that out. I hear yes, but then and that means you get it, but yeah. So I could also just say this, just like the last one, right? So the last one, the base, I just had, what was that, calcium hydroxide or something? So, barium, I'll just do calcium, same thing. And then I'll say this is aqueous. I could also say this is aqueous, and I could do something like this, and I'll get Ca. Actually, this is usually solid, and you put aqueous, you put H2 over here, but that's how they did it, and you end up with this plus this,
H.
right?
Right.
Same thing here. I could just say H plus NO3 minus. As opposed to that where I added the H2O on this side, and then the H2O bound here is the hydronium, which is, this is how it actually exists. But I could write it like this, it's just as
Just put
appropriate.
into water, right?
Right, yeah. I just pulled the water from here, and then I pulled the water out of there, leaving the H plus. Okay, now, I have 0.4 molar here. Since this is strong, goes all the way to completion, what do I have for concentration here and here? For 0.04. 1 to 1, so what do I have here? 0.04 molar. And what about here? 0.04 molar. I care about this one. So I have 0.040 molar. So then can I find out the hydroxide?
Yeah.
Yeah. Can I also already determine whether or not it's acidic or basic solution?
Yes.
Which was
It is.
acidic because that's greater than 1 times 10 to the minus 7. So I have a greater hydronium ion concentration than hydroxide, which creates an acidic solution. And then, of course, it's just 1 times 10 to the minus 14 divided by 0.040. And that gives me my hydroxide concentration. See, it's much less, that's much more. Therefore, it's an acidic solution because that's the indicator of an acidic solution, the H3O plus or the hydronium ion.
Acidic.
Is that okay?
Mm-hmm.
Oh, we got another one. So here we're just going to identify whether or not these are acidic or neutral or basic solutions. So I guess it's saying I have a hydroxide concentration of 1 times 10 to the minus 5 molar. Would that be a solution that is neutral, acidic, or basic? Basic, because this is greater than what?
1 times 10 to the minus
1.0 times 10 to the minus 7. Since that's greater, then this must be a basic solution.
Well,
What about this? Is that greater or less than 1.0 times 10 to the minus 7?
less than
Less than, so what kind of solution do I have?
acidic.
This is looking at the acid, so that means this is less, so that means I have a
Acid.
basic solution.
Okay.
Absolutely.
Mm,
Right?
right.
Is this greater or less than 1.0 times 10 to the minus 7? Greater, so
Greater.
therefore I now have a what kind
Acidic,
of
yeah.
acidic, absolutely.
Looking at the acid.
Okay.
Because H3O is an acid, is that what you're saying?
Okay, the very fundamental thing that we're talking about here in terms of acidic and basic, if you have H3O plus or hydronium ion, you have an acidic solution. If you have hydroxide ion, you have a basic solution. So if they're in a neutral state, they're equal to 1.0 times 10 to the minus 7. So if I have greater of one than the other,
Yes.
then it's that type of solution. So if I have more H3O plus, it's got to be acidic. If I have more OH minus, it's got to be basic. And it's relative to 1.0 times 10 to the minus 7. So this is greater than 1.0 times 10 to the minus 7. It's hydronium. It must be acidic. Right? Is that okay? What about this? Is that greater or less than 1.0 times 10 to the minus 7?
Less than?
Less than, and this would be for a
Basic.
base, so then this solution is
Acidic.
acidic.
Nice.
It's okay. By the way, I did this with you on the first two examples so that you get a feeling for it off an actual question, right? So we determined whether that was acidic or basic that way. This is just one way to determine this, by the way. It's the only way we know at this point, because I haven't converted this to pH yet. Yeah, is that next? Okay. Oh, pH scale, good, next. So the problem with this here is what? When I look at these numbers, do they stand out as real obvious types of, is it really easy to read?
No.
No, it's a little challenging to read. So we created a pH scale, which is just an easier way to read these kinds of numbers. It just makes them more simple, okay? And probably what some of you are familiar with anyways. So the pH scale is just the logarithm to the base 10. So I say the pH of something is equal to the negative log to the base 10 of the concentration of the hydronium ion. That's what the pH is. And if I wanted the pOH, then it would be the same thing, except for it would be the concentration of the hydroxide ion. That'd be the pOH scale. So then on the pH scale, the lower, at 7 you're at neutral. Below 7 and the lower you go, the more acidic you are. The higher you go, the more basic you are. On the pOH scale, it's the exact opposite. The lower 7 is still neutral.
Right.
When I go below 7, it's now more
Acidic.
basic.
Basic.
And when I go above it, it's more acidic. So depending on whether you're looking at the pH or the pOH scale. Okay?
Oh, okay.
So here, as an example, let's say the concentration of the hydronium ion is 1 times 10 to the minus 3. By the way, just knowing this, do I already know if it's an acidic or basic solution?
Yeah.
Yeah, it's an acidic, right? Because that's greater than 1.0 times 10 to the minus 7.
Right.
Now, I can obviously figure that out with a pH scale as well, but I can do it here. I plug this into here, and then I put in my calculator this. Remember, there is a negative here. So you put in this in the log, gives you 3.00. And then you have a negative, and this comes out negative. Negative times negative is positive. So the pH is actually 3.00, which is less than 7, and therefore you know acidic.
Acidic, yeah.
The only other thing I'll point out here is when you're dealing with logarithms and sig figs, in the concentration you have how many sig figs here?
2?
2. So then when you get the number out of your logarithm, you go from the decimal that number over. Does not matter how many are on the left side of the decimal, only here. So if I have 2 here, that means I go 3.1200.
Right.
That means if I'm going from if I'm inverting this, the invert of the log of this, then this would go 2 here, I'd end up with 2 here. Okay, that's how you convert sig figs in logarithm scales. Okay. Oh, they do it next? Okay. So there's your 2 and your 2 to the right of the decimal. If I'm going this way, I see how many are to the right of the decimal. That's how many I put into my coefficient. Is this okay? Just no problem? I think we did this also in 101 or something for some function. Go ahead.
So it's neutral at pH 7 because when you plug in 1.0
1.0 times 10 to the minus 7, you get 7. Absolutely, yes. Whether it's OH or pH, or POH or pH. Yeah, they're both the same. Right? Yep. Okay, so solutions. Concentration is 1.0 times 10 to the minus 7. The pH is 7. Okay. In acidic solutions, the concentration of H3O plus is greater than 1.0 times 10 to the minus 7, and therefore less than 7 on the pH scale. And for basic solutions, what am I gonna say here?
The same.
This is going to be less than 1.0 times 10 to the minus 7? Or more than? BH30 plus.
Right. Less than.
Less than.
Right.
And the pH will be
Less
greater than.
Oh, for basic, just kidding.
And remember, this is the pH. If this was the pOH, it would be all inverted.
Mm-hmm.
Keep that in mind, right? Okay, so here we go. I guess here's just some general common substances, and they're different pHs, so you can see how acidic they are or basic. Human blood, close to neutral. Egg whites, and all the way over here, milk of magnesia, household ammonia. This is just magnesium, just so you know. And then these are all basic kind of things, and of course sodium hydroxide would make plenty of sense there. Beers, if you like beer, wine, and some good stuff. If you don't like either of those, maybe you like soft drinks. You can see soft drinks are actually more acidic than wine or beer, but probably a little less filling. So you can take a quick look at these things, and you can just kind of gauge just some basic stuff that you have, you know, that you eat, drink, whatever, every day, or you know, throughout the year.
The sweeter and the bitter that it is, that's different than that, right?
Yeah.
Okay.
Because that is sugar, but sugar can contribute to that. We're going to see all kinds of ways to contribute to basic basicity or acidity of solutions as we go through. You'll see that some things that you didn't expect actually will create some level of that.
Acidity, right?
Yeah. But then, you know, in some of these things, you have a lot more than just one thing in it.
Right.
So then they're focusing on, and these are going to be general average. That's why you see the range here, which I like a lot better. A lot of times you'll see textbooks that will say 2.3, and you're like, every lemon is 2.3. Really, that doesn't make any sense, right? They're all going to be in a range.
What does pH stand for?
Power of hydrogen?
What?
Power of hydrogen?
I mean, what does the P stand for? The H is just the hydrogen.
Yeah.
So the power of the proton.
The actual term, I don't know if it actually does have a term.
Yeah, they say
It
they
translates directly to the logarithm base 10. And for whatever reason, anytime you take it, not the natural logarithm, but the base 10, and I can't recall if it actually has if the P has a name or it's just the connection, but like that's just how it was defined.
It says potential.
Does it?
Yeah, it just goes
So you can send potential.
Yeah, they call it power
Yeah.
potential.
Yeah, because you're going to see that in a lot of things. You're going to see that with the equilibrium constants.
Yeah.
And the Ka, you'll see pKs, and that will matter. You'll see POHs. So it's anything associated with the natural log, or the base of the 10 log. So yeah, whether or not, I guess if that's the name, what did you say?
It said potential.
Potential. But see, that's odd because we're going to get later on into electrochemistry,
Yeah.
like at the end of the semester, and there we deal with electropotentials, and that's where I'm not so sure that's a good way to really think about. I just call it P. Yeah, I wouldn't worry about the name here. You can if that's what it really means, but okay. So let's see. Lower pH is obviously more acidic,
Yep.
which means it has a greater concentration of hydronium ions in it. Change in pH equals 1, which would be equal to the change in the hydronium ion as going up by 10 because it's to the base 10. Okay. So here, relationship I mentioned before, on the pH scale, the lower you are, the more acidic. At 7, you're neutral, and the higher you are, you're more basic, all the way up to 14. And then if you look at the concentration of the hydronium ion, it's, you're looking here would be the higher concentration. As you go this way, it'd be lower concentration, and this would be the neutral 10 to the minus 7. And also, usually you see this is kind of faded here, but usually over here where it's more acidic, you'll see red, and where it's more basic, you'll see blue. Those are the general color schemes for what you're looking at. So in between here, you see it's kind of in between a blue and a red, red at the neutral spot. Okay. Obtain the pH corresponding to a hydroxide ion concentration. Okay, now this is just playing around with the same kinds of things. If I have usually there are 2 or 3 ways to do this, okay? I don't care which way you use, just make sure you do it right on the exam. You have it's asking for the pH here, and you have the hydroxide ion concentration.
Right.
Now, I haven't talked about the POH, and I don't know if it does. I think I mentioned it. I could just get the POH, and then say 14 minus the POH gives me the pH. That's one way to do this. Okay. Or I could convert the hydroxide ion concentration into the hydronium ion concentration and then solve for the pH.
Mm-hmm.
Right? Negative log of the H3O concentration.
Right.
So it doesn't matter which way you do it. I'm assuming they're going to go here, but if I convert this to the hydronium concentration, it's just the Kw divided by that. That gives me the hydronium concentration. Then I say negative log of that concentration, that's the pH. Okay. So let's go ahead and do that. 3.7 times 10 to the minus 5. I plug that in here. I get the pH, and I have 2 sig figs there, so I have 2 from the decimal, gives me 4.43. That's the pH. Okay. Like I said, the alternative way to do this would be to get the POH, so this would be the POH of the negative log of this, and then say 14 minus that gives me the pH. That'd be the alternative way. Doesn't really matter which one you do. Okay. So this isn't too challenging. I think this was not taught in Chem 101, right? Or 65?
No.
That's interesting, because we teach this in Chem 51, which is kind of an intro. Yeah, so that's why I'm assuming that you guys this is not going to be too challenging. You guys are much more advanced than Chem 51 students. That's like the equivalent of Chem 65, except for it's got a biological twist to it, because most of them are going to be nurses, so they need to know how to do stuff like this. But that's all this is. This is nothing really overly challenging for 101 students. This is going to be the same thing. So here I have the pH, and now I want to know the hydronium ion. So I can convert either the pH, I could say 14 minus that to give me my POH, and then do the inverse of the log. Or I could just do the inverse of the log for this, get the hydronium concentration, and then convert that to the OH concentration. I'm just going backwards. Okay. So here they're going to say, okay, here's the log of this. So that's the, remember it's negative log. So I'd move the negative from here to here. That makes this negative 3.85, and then I take the inverse, which is just the E, right? Huh?
Like base 10.
To the power of, because it's not a natural log.
What's that? What was the question?
Is it 10 to E? 'Cause it's not,
It's log based.
Oh, yeah. This one, just the anti-log. Yeah, the anti-log. So you have the concentration, H3O plus, equals that, which is the same thing as this. By the way, you can't just plug in 10 and then that on your calculator. So make sure you can work your calculator properly. In fact, everybody, let me walk you through this. This gives you the concentration this way, and then now I simply take the KW, whoops. Let's make sure we get this answer here first. Everybody should take out the calculator. Whatever you're going to use on the exam, take out your calculator, and because they're all going to be slightly different in how you do this. Make sure that you get this answer out of this.
Right.
Okay. Some of it's going to be easy. Some of you are going to struggle depending on the type of calculator. TI versus Casio types are different in what you have to put in first or second.
Professor,
Mm-hmm.
I subtracted this and I have the 2 decimals since that is, that's why I put it here.
Yep. That's right.
No, put 10,
Some calculators, the big.
then the little arrow.
Power of.
Put 10? Yeah. No, put 10.
Yeah, you're not using the EE function on this. You're using the anti-log. That's usually the second feature and the log.
Negative 3.8.
Some of you will have to put the number in first. Some of you will put the anti-log in first. It will vary. But you also have to make sure you have to the minus, the negative has to be there. That's why it's brought over here. Anybody not able to get that answer? By the way, this is where it varies a lot from Chem 51, because Chem 51 about 90% can't get this answer. Let's see how quickly you guys all got it. There's a big difference in intellectual levels. Go ahead.
The sig figs for this was based on.
How many? So here, how many from the decimal? 2, and so therefore this is 2.
So it's the negative.
Oh, negative.
So
Because of the log, no?
pH is going to be 2, whatever is after the
Okay, it's supposed to be negative here.
When you're going from the concentration to the log, then it's however many you have in here in the
Negative
coefficient.
log.
And then it's that many positions after the decimal, once you get it in through the log. Yes.
Because they didn't put it over here. So they divided by 1, negative 1. They divided by negative 1, so then this becomes negative 1. If it was positive originally, so it was like this. So
Everybody
this is
okay?
negative equals
If you're not,
3
come to
point-
my office, I'll figure out some calculators I might not know. I might have to, some of them get real tricky,
No,
they're
they
real
put it on the
awkward.
outside already.
They don't have a lot of features,
So
which
how
makes
do
it,
they
you gotta
negative
figure
over
out
here?
some different way. There can be situations, if you have a basic TI or
This is your
Casio,
pH.
then this shouldn't be too hard, but if you have something a little more challenging, then just come to my office and we'll
This is
figure it out.
negative to get
Okay.
solve for.
Divide negative.
Okay, so now, what did I solve here?
Divided by negative
I
1,
solved for the,
divided by
what?
negative 1.
Hydronium
That's
ion?
what this is negative. This is
So that's it, right?
So the real
That's all I
answer
needed.
is not
The hydronium ion concentration, that's
No,
it.
pero esto.
If it asks for the hydroxide concentration, what would I have to do here in my adjustment?
Wait, so what stands for H2 or just not stands for?
Right, 1 times 10 to the minus 14 divided by this, I'd get my hydroxide concentration. Okay, now what do I have here? A 1.00 liter aqueous solution contains 6.78 grams of barium hydroxide. What is the pH of this solution? Interesting.
solve it like
So how would I find the concentration of this? Convert this to moles, and then I know it's already in a liter. So then I divide by that 1 liter, so it's gonna be whatever the moles are.
Look at this thing.
And then what do I do?
And then
What is it asking for?
write out the equation to see if
The equation, is this a strong base?
How do
It
you
will
solve for this
dissociate
actually?
completely, and how many hydroxides per barium hydroxide? So it would be the concentration of this times 2 would be my hydroxide concentration. Then I can solve for the hydronium concentration, and then put it into the negative log of that concentration. Right, it's okay? Not too bad, good.
So,
So here, let's calculate that, I get this is gonna be this times 2 of those,
that's
and 2
what
of
they're showing
those.
right now.
171.4 grams
It's
per
possible.
mole.
No, it's just-
Divided by the 1
How do
liter,
how
I'm
do
just
you
putting
also
it in here, it's kind of
pull that
awkward.
X equals
Usually,
this?
for me, I'm more comfortable, I'd stop here and get my mole, and then since it's already 1, you already know what the molarity is, but they're actually adding that step here all together, just so you see what they're doing here.
Because
And that
it's
gives me
not Ln.
0.03956 molarity, and I put an underline under
So
the
it's just a
3rd
constant.
position here,
Can you
because there are
solve
3
this
sig
with
figs. But I wanna hold this as I carry it
X
through.
is, which is what this is.
If you didn't, on a problem solving, I wouldn't care. If you just left the 3, that's fine. This is gonna make it a little bit more precise, maybe, maybe not. Usually it's not gonna matter much, and if it does, I'm not gonna worry. If you know this, that's all I care about. Okay, this gives me the hydroxide concentration is gonna be, I should have an equation in here that says, in fact, why don't I do that here, just so you know what I'm looking at. All I have to do is change that to a B,
Which is that.
Okay, pero ¿qué me está preguntando?
And
What
this
happens if
is
there's a
B.
one which is negative 3.85?
and there you go.
Solve
That's essentially what I'm looking at,
for this.
this equation right here. So there's my 2,
The negative
and that's
of
what
that.
the 2 is doing there.
And the negative of this.
That's 0.0791 molarity. I now can convert this. I take 1.0 times 10 to the minus 14 divided by this. That's going to give my hydronium concentration, and I'm going to put that into the pH formula. So there's my hydronium concentration. Now let's just plug it into the pH formula, and that gives me, so I have 4 sig figs. So this is wrong because, oh no, 3, because the underline. So this should be 3 from the decimal. That gives me 12.898. That's my pH. And now I would ask, potentially, is this an acidic or basic solution?
So we're not gonna go, we don't go with the 6.78 to determine the sig figs?
How many are there?
2?
Oh, yeah, you do, but like this.
How many are there?
No, 6.3.
3.
Yeah.
How many are here? What's that that underline's representing 3?
Yeah.
3? 1, 2, 3. So we did go with it.
So be basic?
Hmm?
Basic?
This would be basic, absolutely.
Less
pH
than
is high,
-7, right.
above 7. So it'd be, and of course, we could have figured that out here because the hydronium concentration is very, very low, or much lower than 1.0 times 10 to the minus 7. So that would make it basic. So there are multiple ways you could determine the basicity or acidity of this solution, right?
Cool.
Is that okay? And we would expect it to be basic since we're looking at a
Oh, yeah.
hydroxide. Absolutely.
Can you go back one slide just for a second?
So I didn't lay this out very well. This is really what I'm looking at here, right? So I have the concentration of this at that, right there. But see, this would be the same concentration, this would be 2 times it, which is where that comes from. So if you lay it out here, you could see where that 2 comes from a little easier. It comes from that 2 there, but this is a little easier to see with the coefficient,
Okay, the average.
right? Any questions? Comments? Okay, okay. Next slide. And I'll just lay it all out there. I think that's, and I'll let you guys let me know when I can move on.
Ready?
Okay? Good, okay. Okay, oh, we got another example, wow. Okay, just in case we haven't figured it out by now. What is the mass? So here it's asking for the mass of the HI in a solution with a volume of this and a pH of that. Okay. So what do? Let's just talk strategy. You look this over, it's asking for a mass. I have this and I have this, so let's start with this here. Well, actually, what would I start with here? What would be the best strategy to start with to lay out this problem to better evaluate what it is I'm trying to solve for?
And first find your concentration.
Let's do equation. HI, is that a strong or weak acid? Strong? So I have HI, and it's aqueous, it's going to go to H plus I minus. Everybody comfortable with that? Okay. What is this representing here?
H3O plus
Hydronium ion. So can I find that with any data in here?
Yes.
Yes. What?
Take the end.
From the pH. The pH equals the negative log of that. That's what we're doing here. I'm tying this in right now because this is really important where people get lost. This is where we go beyond what a Chem 51 student does. All they do is that basic, simple manipulation between going from here to here. They never have to worry about equations.
Right.
We just say you have H3O plus concentration, what is your hydroxide concentration? But I'm saying, whoa, what I want you to be able to do is this. Because this should identify what you're solving for here. And this is exactly what we're gonna do. So these are all, so far you notice everything I've given you is what? Acid base are always strong. How would we deal with this if they were weak?
Would be the equilibrium.
What is the key here? You must know this equation is what translates to this, so that you're looking for this. And if it was in an equilibrium, then you do an ice chart on it.
Right.
Since it's all one way, we're simply saying, well, if you know the concentration of this and this, the coefficients all match. If it's in an equilibrium, they don't match anymore. We're dealing with x's and stuff, right?
Right.
So the key here at this stage is to recognize, I keep emphasizing this as strong, complete separation. It means that whatever the concentration I have here, it's got to be the same based on the coefficient ratio, because it all goes to completion. If it doesn't all go to completion, well, that doesn't hold up, because this is going to have a lot more than this, right? In an equilibrium. And I solved that through ice. The other thing I'm saying is that now that I know what the pH is and the pOH, so let me put this up since they didn't show it. I thought they would. This is equal to, see that? So if I have one or the other, I can solve for this, and if this breaks up as an acid, I can solve for that. If it breaks up as a base, I can solve for the hydroxide.
They go into POH in the next section.
Okay, good, so they will. Does everybody recognize that? So if I have the pH here, I can solve for this, which I do at 1.25, which means that if I know this, then what? I know what the concentration of this is through this ratio.
Right.
And you have your.
And then I have my volume, so then I can I could use that volume and the concentration as a conversion factor to solve for the moles, and from the moles, I use the molar mass to solve for the mass.
Yeah.
Right.
But I must know this and how to get this from it.
So you would just put 1.25 for pH equal to the negative log, and then do 10 to the.
Absolutely.
Okay, and then convert.
Look.
That's exactly right. just in case when you guys were doing it, you know, earlier, it followed. But now it has a reason for doing it. Not just simply to say, is this acidic or basic? That was pretty simple, right? That's the Chem 51 level. This is not so, now I gotta recognize what am I solving for in here, and can I solve for it? Or if I have this, can I figure out the pH from this? If I know the concentration here, yeah, absolutely. See, we don't put this in the context of solving for things in 51. We just say, here's a hydroxide or here's a hydronium, solve for one or the other, here's KW, and that's it. Is it basic or acidic? I'm saying you need to recognize here what you have here. What if I have two acids? Then and they're both strong. What if one's weak and one's strong? What if they're both weak? We're going to get into a bunch of fun scenarios, right? In solving for the pH. This is just the basics we just went through. Now I'm saying, but you must know these equations, which remember I've emphasized for a while now, because you need to figure out what it is you're solving for, and then we'll figure out, and I'll help you figure out the context that you're solving it in based on what you have in your solution. So far, just a strong acid and a strong base, that's all we've seen. But I'm now making that early correlation between a strong acid and figuring out what the pH is relative to that. Okay. This is important because if you're lost at this stage, as we move forward, it's going to get much, much more murky in your brain. So as long as you understand this, you'll be okay. So I solve for the pH here, or the H30 plus, I get 0.056.
From
Which means that, well, see, okay, now, what they're not doing here, and so these are the same, that's because if you break down this equation, you have a 1-to-1. That's why they're both equal here. I would always write this, even though I don't do it on these slides.
the equation.
Once I know this, everything's easier. By the way, this is extremely important when we get into the equilibriums, because when you do the ice chart, you need to see what you're doing the ice chart on.
Goes to OH.
I
mean,
they
BA
divide by the
plus OH, 2OH.
What's that?
the 250 liters.
Oh, I don't think.
BA is 2 plus.
That's just.
All we've done so far, knowing this equation here,
So,
is that we
just
figured
take
out that the concentration of this is 0.056 molar, right?
It's these times.
From that, we could then use this
It's not a
to
1-to-1.
figure out what the moles of this are. And from the moles, we could then use the molar mass to figure out what the mass is.
Because I thought you needed the liters to go, because I thought once you do the negative anti-law, then that gives you the moles.
Concentration. See, okay, this is interesting.
Oh, never mind.
Just so everybody knows this, maybe I didn't say this. Maybe I did last week, maybe I didn't, but make this clear. When you see a formula in these brackets, that means it's a concentration.
Right.
Okay, maybe I didn't mention that. So anytime you see these brackets, this is a concentration inside of here. Usually that concentration you could always assume is going to be molarity,
Right.
at least for the purposes of this class. It could obviously be something else, normality, percent mass over mass. We're not going to do any of those things, plus it doesn't work necessarily for pHs. So we're always going to look at this as the molarity. But the brackets themselves mean you're dealing with the molarity or concentration.
Like the ice charts.
Really important point.
Yeah.
So now that I have the concentration here, I could now use the volume that I have total to figure out the moles of this. Then I could just go to the periodic table, I could figure out the molar mass of HI, and from the moles I could take it to the mass, which ultimately is what it's asking me for. When you see mass, you're looking at grams. Okay. So here's my concentration times my volume. Volumes cancel. That gives me my moles. Here's my molar mass. Grams over mole. That gives me my mass. And I get 1.8 grams. So that means that if I have HI in a solution with a volume of 250 milliliters and the pH is 1.25, I have 1.8 grams of hydroiodic acid. Okay, so we get a little bit more challenging, but this shouldn't, this is a lot of, the back end here, this is really just Chem 101, right?
Chem 65.
Solution stoichiometry kind of stuff here, and this is kind of goes along with just your regular molar mass
Isn't that
conversion.
65?
Right, 65. But up here, this is a little bit new, and now you're using all this information in the context of this and your knowledge of strengths. Because if this is a strong acid, that's why this works. That's important. I keep mentioning that because that's where I see people get stuck. If it's a weak acid, we can't do this. At least not yet. You actually can
The eye shot.
with your knowledge set, but we haven't covered it formally yet. Okay. This is presuming that this is a strong acid. That makes this really easy because it's a one-to-one. It's whatever these are here. If it's a weak, it's not that way. It's clearly going to be less of this than what you have here. Okay. And it's going to be in an equilibrium, so I have to do an ice chart. And I have to find the equilibrium amounts in order to determine what all this stuff is. Okay, okay, so here's a POH scale that I was talking about here. So this is a POH, same thing, nothing big there. Solve it the same way you solve the pH, no big deal. Same thing here. Now, the pH is this way, looking at this scale. Here's this more acidic, here's the neutral, there's more basic. But it's the exact opposite for the POH. Okay? That's all it's saying. At the lower end here, it's more basic if it's the POH. At 7, it's still neutral. And higher is going to be more acidic. They just invert, that's all. The scales invert pH to POH, which should make plenty of sense. Okay. The relationship, we already know the concentration relationship relative to the KW. If I take the log of both sides of these here, if I take the log of this and the log of that, this gives me minus 14. This breaks up into this log plus that log. Then I move the negative through both sides. And this is the pH, this is the POH. So I could simply say the pH plus the POH equals 14. And that's the thing I was saying before. If I had the pH and I needed the POH, I take 14 minus it. If I had the POH and I wanted the pH, I take 14 minus that to get this. The only kind of question that I think can come up for somebody who hasn't used this very often is depending on the sig figs of this if I have or this that I have, I just make this that number of sig figs. Okay. This isn't obviously set at 0.0. So in other words, if I think one example we had, what, 6.989 or 898 or whatever, then I just add the extra 0 there and subtract out relative to that for the sig fig use. Okay, another one, we're going to talk about this one a lot, I think, the pKa. So there, once again, just take the negative log of the Ka. What is the Ka? That's the acid equilibrium constant. Of course, we haven't talked about that yet because all we've looked at were things related to strong acids, strong bases. They don't have Kas or Kbs.
We
right?
used that in lab today.
Yes. But when we do get to the Ka, Kb, we need that in order to determine what the concentrations of things are. Remember when we did the Kcs? Same idea.
Mm-hmm.
I could use X for the change, and then I could use X plus whatever my original concentration was, or minus 2X, or plus 2X, or whatever. And then I take that and I put it in my Kc equation. I'm going to do that same thing with the Ka. But then if I have the Ka or the pKa, I could also evaluate how something is in the same context.
In lab, we saw that the pH was equal to the pKa.
Okay, so we'll talk a little bit about those things. Okay. pH will equal pKa depending on the weakness of the acid and other things in there.
Okay.
Right. Okay, so the pKa is just another way to quantify the strength. So are we going to get into a full thing? Okay, I guess we're going to now talk a little bit more about pKa before we get into equilibriums. But this is all in, the odd thing about this is we're looking at other P scales, but we're looking at, so we looked at the pH and the POH. Now, just because we're talking about other P scales, we're going to look at the pKa, but we haven't actually talked about Ka in the context of an equilibrium of an acid appropriately yet, with the pH or the POH. Okay. So we're just going to do a little side thing here, talk about the pKa, which is just this, right? It's the negative log of the Ka. And the smaller the pKa, the stronger the acid. Okay. So just looking at these, what do you know? Is this a strong or weak acid?
Weak.
What about this one?
Weak.
They're both weak. Okay.
Yeah.
Okay. Now, why do you already know that they're both weak?
The oxygen to hydrogen.
there's more.
Do you have a Ka for a strong acid?
Oh, they're
Oh.
No.
Right.
There's no Ka. Okay, see how I'm framing this intentionally. There's no Ka for a strong acid.
Right.
So when we're dealing with the pKs, they gotta be weak.
Equilibrium, right.
So what are we looking at here? We're looking at the strength of the weak acids.
Right.
Right?
Uh-huh.
Keep that in mind. That's really, really important in understanding, like, otherwise you get confused. Is it strong, weak? When they say strong, you're instantly thinking that's a strong acid compared to the other one.
Right.
It is compared to the other one, but it's not a strong acid ever if you have the Ka.
Okay.
It's automatically a weak acid. So this is a weak acid and another weak acid, and what I'm really saying when I'm comparing the pKa's, I'm looking for the stronger weak acid, right? That's essentially what I'm saying here. So keep that in mind as we go through. Okay, so then the smaller the pK, so what do I have here? This is Ka of 1.1 times 10 to the minus 2. This is 1.8 times 10 to the minus 4. So the very next thing I want to say is when we look at the Ka, we're looking at the products over the reactants in that equilibrium, presumably, right? Even though that could flip if you flipped it, right? And that means, oh, if I'm looking at something like this here, this is in the top half, not the bottom half, right? And this is what's indicating the acidity.
Right.
So the greater of this is going to be
More base, more acid.
a stronger weak acid.
Right.
It flips with the pKa, which means the lower the pKa, which is what it's saying here,
The stronger the acid.
the stronger the acid. Okay? That's how it works. And I have to even say it slowly because I'll get confused. Because it's confusing, right? So if you say it slow and you fit it in the categories I just did, you'll get it right. Otherwise, a multiple choice question is going to blow up on you, right? You can see how that could be a pretty tricky kind of multiple choice question.
So say that again. You say H, the greater it is.
So how did I do this? The first thing I said is, if I looked at a Ka,
Right.
for example here,
Mhm.
I would see this, right? If I looked at this, the greater this, the higher that.
Right.
When I put it into the pKa, then it flips, right?
Mhm.
Just like that chart we saw alongside with the pH and the H+. They flip. So then the higher the Ka, the lower the pKa, the stronger the acid. You have to put it in those categories, otherwise you'll easily be all over the place. Like I said, since I don't use this regularly, I have to say it slow and put it in this context. This is what helps me make sure I get it right, right? Because it's not a natural thing. It's not something you were born knowing. It's not something that's instinctual. It just, if I know, as you guys are just learning these things and these terms as of this semester, because I don't think we've ever really talked about Kas or K anything prior to this. So you put it in this context, you see where that relationship is, and then you say, okay, I'm taking the logarithmic scale of it, then I know that's got to be the inverse of that.
Right.
Okay, so then here, which one's higher?
The one on the bottom.
This one's higher than this?
Oh yeah.
So
Yeah,
then,
it's lower.
which one is going to have a lower pKa?
The one on the bottom. Wait.
This one?
Yeah.
That's what we just said.
All right.
And therefore, this
Higher
is
than
going to
lower.
be the stronger acid.
Stronger.
Okay. Is that okay? Okay.
Okay.
Hopefully that makes sense, and if you're stuck on an exam, hopefully you think about exactly how I just said it to help yourself. Draw this out if you have to. This gives you the foundation to work off of. From there, you should be able to figure it out. If you just try to do it in your head and let things float around, then, you know, I guess you have, what, a 25% chance? Right? Got to get one of them right if you put something. Okay. So let's rank the following. These are 0.1 molar solutions, so I'm not changing the concentration. And we want an order of increasing ionization, meaning what?
Dissociation.
Strongest weak acid is going to dissociate more. Okay. So I have the Kas here. Which one is the highest Ka?
The HNO2.
7.2.
HNO2. So this would be the what?
Really
Lowest
lowest.
pKa, and therefore the strongest one.
Right.
So this is going to ionize what? The most.
Right.
Okay. And so it's going to go from, I want to order this increasing, so that would be the last one. So the first one would be this. This would be the weakest of them. Then it would go to this, then that, right?
It goes from first, and then this bottom, and then the strong part.
It goes from here to there, to there, to there. This is lower than this. Or am I getting that wrong? Oh, that's 8, not 7? Yeah, so it'd go here to here,
Yeah.
to there, to there.
Okay.
That looked like a 7 from my angle. So it goes here to here, to there, yes.
Okay, I was trying to
Yeah.
think.
Yeah,
what
that looked
to
like a
say.
7, so 2.9 times 10 to the minus 7 is greater than 1.0 times 10 to the minus 7. But then when I turn my head further over, I see the 8, not 7.
Okay.
Okay, so it looks like this.
Rank them. Which one is the lowest PKA? PKA.
And
Mhm.
the redder usually means more acidic. Remember I mentioned that earlier, just to give, in this case it goes to yellow because, why yellow and not to blue?
Because it's not.
Because they're all acids. Yes. Okay, and once again, these are just ranking the strength of weak acids relative to each other. Because remember, in 101 or whatever we talked about strong and weak, weaks were always the same, right? There was no distinction. About 5%, I would say, ionized, all of them. Sometimes I'd say 4 or 6. It was always a low number. So now we're going to actually determine which ones are lower or higher relative to each other. Okay. Moving on. What do I have here? Rank the following same. By the way, since it's up here, you see how the other group said 0.1 molar too? You got to be comparing the same concentrations, right? If I increase the concentrations, you would expect then I'm going to have more H pluses,
Yeah.
right? Or if I decrease it so much, I might not get any. So I got to compare across the board. And I could potentially put so much in that now they have more intermolecular interactions with each other and therefore become even weaker, by the way. It doesn't always have to be that intuitive where you put in more, it's going to have more H pluses. Okay. But that's why they're always the same kind. It's not really relevant, it's kind of assumed, but because I'm putting it up there, you should have a sense of why that's up there, okay, even though it's not part of the actual problem here. So here I'm ranking the acids in order of decreasing this. Okay. So the higher ones of this is going to be the lower pKa.
Mhm.
So that's going to be the most, or the highest H plus concentration, then that, then that, then that. And I want to increase order of decreasing this. So that's how I would do it. So I'd start here, there, or here, there, there. Okay, so that's the lowest, that's the highest. Once again, set up a Ka chart like this so that you can see that the H plus is on top, so that you could look at the Ka increasing with higher H plus concentrations or hydronium concentrations, either way you want to say it, and therefore the pK would be lower. So I get this. Okay. Okay. Hopefully this helps. This is the key to like giving you some placement of it all. Otherwise, like I said, you kind of free float it and try to just go through it in your head without looking at something like this. It gets more confusing. Okay, now, calculating the pH of strong and weak acids. Okay, so there are a couple things. Let's see where we're going. We haven't really done weak acids on its own, but we did do the strong acid already. That's what we've done. And then at some point we're going to get into strong and weak together. So let's see where they're taking us here. This is just containing either a strong or a weak acid. So this, we've already done the strong here. So you're looking at the ionization of the acid. So you look at something like this here, and this is going to be a weak acid ionization because I have the equilibrium, right? So the HA is the acid, H2O. You get the H2O plus or A minus. You could also just say HA goes to H plus and A minus. Okay. And you get the autoionization of the water, which is what, 1.0 times 10 to the minus 7, if you recall, right? Now, the ionization of the acid is usually going to be a lot more than the autoionization of the water by itself. But when I say autoionization of water, I'm referring to H2O on its own. So you're going to have some of the H2O self-ionizing itself the way we looked at it originally, which was what, 2 H2Os gives you an equilibrium of H3O plus and OH minus. That's the autoionization. That's the 1.0 times 10 to the minus 7. So I'm going to have some H's from that, but I'm also going to have H's from the ionization of the acid itself. And this is going to be a lot more than this. So usually this is going to be ignored. Okay, I'll just set that out now so we don't have to waste too much time on the autoionization of water. But it does exist. I think that's all they want you to know. And that's the, oh, that's right here. So here's the autoionization of water, the autoionization of the acid. You have both pieces here as the acid. That's all it's saying in a solution. In a solution, of course, where the solvent is water, right? Because if I make the solvent something else, then this not only does not, that who knows what actually exists in its own autoionization, and that changes how much of this you're going to have because you don't have the H2O, you have something else there. So this is only in the context of water, keep that in mind, which is usually what the solvent is in most solutions, but it does not have to be. Okay, so of course your KW is this. So, unless I'm dealing with extremely dilute solutions, which I just pointed, so let's say 0.0001 molar, so I have very little of the acid, let's say, in there, then the autoionization water does not really add to that H3O plus amount. Okay, so that's not a big deal. I think I brought this up last time. So, if I have this going on, okay, so I have a solution of this acid, which is generic acid here, and you have this happening. And then you have the autoionization of water here. As I increase this, what is that going to do to this, based on what we learned early on?
Increase it.
The Chatelier's principle, it's going to shift it back, so you're going to have even less of that.
Right.
That's all that next statement is saying, right?
Yeah.
So because you have so small of this already, and now you're producing this, this is going to, this is all in the same container, this will now shift this back towards the H2O, which will shove it back in there. And that will shift it a little bit more this way, and they'll balance it out. Basically, all you're going to have is this and none of that. That's what the point is. So that's what this is saying. So most strong weak acid solutions, and this is what I told you early on, just ignore the amount of H3O plus produced in autoionization, as well as the OH minus when we get to the bases. But just so you know it exists. So we seem to have gone through 3 or 4 slides of a discussion about what is there, but don't worry about it. That's the autoionization of water. Yes, just know that's happening. Okay. So this is what we've already experienced. So the H3O plus is equal to the acid because it's all completely ionized. That's what we experienced over here in our previous stuff. So 0.1 molar HCl is the same as the 0.1 molar H3O plus, and therefore the pH is going to be 1. Now we get to do something different. So now what happens if we have a weak acid? Okay, we already know how to deal with a strong acid. So we're going to look at the H3O plus ion concentration of weak acids, not just strong acids. So now the H2O does not equal the concentration of the HA. In fact, it's going to be much, much what? Less. Absolutely. Right? So this is going to be, if this is a 0.1 molar of acidic acid, which is a weak acid, then the concentration of the H2O is going to be much less than 0.1 molar. Okay? Because it's weak. If it was strong, it would equal it. Hence the big distinction of what we did before and what we're now going to do. Also, why you have to recognize if you're dealing with a weak or strong acid or base. So in this case, the pH is 2.87. But if I know that, then what else can I figure out from this?
Minority?
I can figure out that concentration, right?
Right.
If I can figure out that concentration, I know this concentration,
Ice chart?
then the ice chart will work, right?
Right.
Okay. So a 0.1 molar solution of acidic acid is less acidic, higher pH than a 0.1 molar HCl, because this is a weak acid and that's a strong acid. So this would be all the way to completion at 0.10. But since it's weak, it's not all the way at 1.0, it's 2.87, it's above it. So then we want to figure out exactly what is its concentration, but that's pretty easy when we have this, and we have ice charts. So let's take a look. This you can read, all the same things we're talking about. You have to know this kind of equation, right? That's this thing here. Have to now put it in, because, but now the difference here is here and this. So now a lot of other things matter here.
Right.
Here's my ice table. Okay, now we're going to actually apply this in different ways. So my initial in that example, I have 0.10, 0 approximately. Why approximately there? Because of the autoionization, absolutely, but we're not accounting for it, so it doesn't matter. And 0 here, right, of the conjugate base. The change, minus x, plus x, plus x. Equilibrium, 0.1, minus x, x, and x. Okay? Nothing new there for you. Okay. Now, what's going on here? Okay, here's my Ka. And we could use, so if we, the same way you solved for the KCs, you do the same thing with the Ka, exactly the same in terms of the ice chart. Okay? That's probably the easiest way to state it. So that, in other words, there's nothing scary here. There's nothing new. Everything's what you already know. It's just being applied to acids and bases. Okay. So something like this and this. Now, there is going to be one difference, though. Okay, and let's take a look. X, so when we looked at the KCs in equilibriums, what was one thing we can say? The KCs, just looking at KCs. Some of them were favoring the product. Some of them favored the reactant, right? That was something we said with KC. With weak acids, how would we adjust that statement, and weak bases, by the way, in these equilibriums? Is anything ever going to favor the product?
No.
They're weak.
The
No, usually not.
Right.
We're dealing with things that are going to be favoring
Acids and bases.
the reactants.
Right.
Okay? That's really, really important in what they're getting at here. So the Ka is this, right? But this is going to be, is this going to be large or small? Let me put that also. For acids, remember, Ka is reference acid, Kb will reference bases. So I'm going to say the same for both. They're going to be, is it going to favor this side or this side if it's weak? That's what, if it's an acid.
It's gonna favor the
The
reactant.
left side.
Yes, so what's it going to be, small or weak? Small or large?
Small.
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 These numbers are going to be pretty small, right? So that means that this number is what relative to the x? Large, much bigger. Really, really important, because if x is much bigger, I'm sorry, x is much smaller than this number, then does that x matter there?
No.
No. So I could just cancel it out. I don't need it there. The minus x will, is an estimation, is going to be so insignificant that it's not going to matter. What do I mean by that? So for example, when we looked at subatomic particles, and we looked at electrons, neutrons, protons, remember that? The masses of those, the proton and neutron, were pretty large compared to the electron.
Oh, yeah.
So then when we calculate the mass, do we include the electron?
No.
Why?
It's so small.
That's what I'm saying here with the x. Same concept. Okay? So then in these problems, I could automatically assume, now not for Kc necessarily, right? That's an equilibrium not necessarily of an acid base, so it's not necessarily weak or strong. It's just, it's in an equilibrium and you don't know which side it's favoring. But for a weak acid or base, they're usually going to be favoring the reactant side, because that's why they're weak. There's not a lot of these going on. That's why we just categorize the strongest of the weak acids, right? That's why I phrased it that way. So keep that in mind, that makes this x somewhat insignificant in most cases. Now, if you can solve it and you have it, you can use it. Sometimes it could make a very small difference, but if you don't have it, then you just cancel it out.
So in the ice chart, under the change column, would you write just like?
Write it out, and then when you put it into the Ka, cancel it. And we'll do some examples. So I'll show you more specifically what I mean by that. But that's what this is saying. The x is so much smaller than the concentration that I can just cancel it out. Because essentially 0.10 minus x is about approximately, that's what that little thing is, 0.10. So that means this is probably 0.0005. If I take 0.10 minus 0.0005, it's still 0.01 or 0.1.
Yeah.
That's kind of what I'm saying. Okay. So you look here, then I could just say, I could cancel that out. And now I don't need to use the quadratic equation as often for acids or bases.
Yeah.
That's kind of nice, right? I just canceled that out, and I just made it much easier.
Just the square root.
Equation. Yeah, I just made it easy. Now I just need these x's because this is how I'm going to determine what these are.
Right.
That makes sense? Everybody see that? So I slow down on where the key points are and where people can get confused. And then it's just, hey, now it's just status quo. Do what you do, what you already know how to do, the ice charts. So they call this the approximation method. Once again, do these terms really matter? No. Do you know how to use them? Yes, that matters, obviously. Right? Highly unlikely I'm going to say, what is the approximation method? Unless it's coming off an old lab or an old exam where I just juxtaposed the questions and forgot that that's an old term that's not really used now. In other words, you don't think about this as, oh, okay, I'm going to cancel this out. This is the approximation method. You just do it because you realize what it means, why you're doing it.
Yeah.
How would you describe it in the question, like a multiple choice?
I probably wouldn't. I would just have this as a, solve for Ka. But that's exactly the point. It wouldn't come up as a name. I wouldn't say, use it. If I said the approximation method, it's kind of, if I'm asking to solve for the K, just solve for the K. That's all, right? And make sure you do it appropriately where you cancel that out if you need to. And that's the key. Okay, let's try it. Lactic acid is a weak, so here, claiming it's a weak acid, even though I have 2 more oxygens to hydrogen in this case, but I have a lot more going on here. This is a little bit bigger molecule than the ones we've looked at, and that 2 oxygens or more. So here it's called, I'm saying, if I didn't say it's weak, you could assume it's strong, but I'm stating it's weak here. Is a weak acid found in sour milk. 0.025 molar solution of lactic acid has a pH of 2.75. What is the ionization constant for this acid? And what is the degree of ionization? So that's another new term here. Okay. What's the first thing I want to do?
The equation?
Equation. Very good. That's going to help you a lot by saying that and doing that. Because that sets it, first of all, it does several things, right? One is it gives you a foundation to what it is you're working with. Mm-hmm. 2, it settles you down, and it allows you to now work off of that. So you're not worried about what is it saying, how do I just make an equation? What am I dealing with here? I'm dealing with HC3, H3O3 or H5O3? H5O3.
Since you look,
Okay.
I'm like, haha.
And the very first thing I'm going to say is, okay, this is a weak acid,
Right.
so that means I'm going to do this kind of thing.
Right.
Has to be that thing coming off, right? Plus C3H5O3 minus. Why is this so important? One is because the pH is going to relate, everything's relating to that thing.
Right.
Right? So in any ice chart or whatever, I need to know what these things are, what's happening here. And the degree of ionization means that I need to find this and this, because this divided by that times 100 is my degree of ionization. How much of this ionized? So I take this and I divide it by this times 100. That's my degree percent ionization. Okay, so what do I have? Big difference. If this was just one way, would that make this problem pretty easy?
Yeah.
Yes. Whatever this is, they're all the same.
Exactly.
Everybody see that distinct difference now. They're not going to be the same in this case because it's in an equilibrium. It's also why the Ka now matters, where it wouldn't have mattered. You wouldn't have one otherwise. Okay, so I have 2.025 molar, right?
Mm-hmm.
And that means I have what here?
0.
0 and 0,
Zero.
minus x plus x plus x. 0.025 molar minus x, and x. Now in this case, can I solve for x? Which x, if I can, which x can I solve for? Or does it matter?
The lactic.
For the products.
What do I have? I have what? The pH. Can the pH help me solve for something? What? It can help me find this.
Right.
and more specifically, my equilibrium in my ice chart. Now you see why this equations, by the way, we're going to do where we have multiple steps. So each one you have to know what the equation is that you're referencing in these charts. Okay? But for now, the difference here is that you're looking at this equation and you're given this information, but you actually have enough data to solve for this because of the pH will give you that.
Right.
And is that the pH at equilibrium
At
necessary?
equilibrium, that's the pH of the solution.
Okay.
Absolutely. Right? So then my Ka here is going to be x squared, which I'll solve for here, right? X squared over 0.025 minus x. But if I'm solving for x, I could plug all that in and get my Ka just like that.
Yeah.
Everybody understand what I'm doing here?
Uh-huh.
And why? So let's play this. And then, of course, I'll take this divided by this times 100, and that's my degree ionization. So look here. So remember, you could do this, or you could just add the H2O, and that just makes that H3O plus. It does not matter which one. But in an ice chart, why this way is a little nicer is this a liquid? So then in the ice chart, what's here? Nothing. So if you do that, make sure you know that. I don't have it here, so I don't need to worry about it.
Right.
But if I do have it here, there's nothing in this column because it's a liquid.
took out
It's
the water
not
both
a
sides.
concentration and it's not a gas. Remember that?
Right.
When we developed that through the KC. Now, the other thing is, you see this here, and this may make more sense for what you're used to the log, but I could do this also. It's just H plus, H3O plus, those are essentially the same things.
Right.
Okay, so I like this better simply because everything fits. If you do this, which is perfectly fine, that column has nothing in it. They're just solids because it's a liquid.
Right.
Okay. Okay. My Ka is equal to this, which is the same thing basically as this. You could just put H plus. See, there's still no H2O in there. Yeah, I should, just to double check, I know you guys already know this, but when you do have the Ka, you are talking about the equilibrium concentrations in here. That's the whole point of the Ka.
The book, I mean, the note just says both of the reactants are liquids.
Both what?
Both of the reactants are liquids, not just the H2O.
Both are what?
Both
Aqueous.
of the reactants are liquids.
I think that doesn't
Oh,
talk about
look.
Yeah, this has to be, this is aqueous.
Okay.
Because it's in the water. Right.
Okay.
Right. So now I have, here's that, so see here, theirs has that line, the line in there. Mine doesn't have it, because I didn't bother with the H2O there. I just took it out of that in the hydronium ion. Okay. And we have the same kind of things here, 0.0250, blah, 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 blah. Now we can solve for the Ka this way, right? Same thing we did here. And first, now we can solve directly for this right here, the H3O plus, anti-log of the negative pH, which is 1.78 times 10 to the minus 3. So that goes now in here and here, right? So that's the same thing. Each one of those are now x and x, and this is this minus x. You see how this does, in this case, have a little effect, but if you didn't know what the actual number was there, then you just cancel out that x and assume it didn't matter much. Okay, and then I plug all those things in, and I solve, and that's my Ka. And is it small? It's supposed to be fairly small. But it's actually stronger than the other weak acids. If you recall what their Kas were, they were what? A little bit lower, right? Okay, and now the percent ionization, I take this divided by what I started with times 100. So that's x divided by what you start with. So that's this divided by what you start with times 100, and that's your percent ionization, and it's 7.1%. So now it's not always 5%, right? This case it was 7.1. It could be 4.3. It could be 12.1. It could be a variety of things. It's just a weak acid. That's it. Okay. So the term percent ionization, I do ask this kind of question on an exam. And of course you're going to have to do something like this, but it will get more challenging than this. This is just, we're just getting started. promise that. But it won't be beyond the scope of what you know. The key here is getting the foundation and this part down. If you understand this through what I'm saying, especially with the equations, then the rest, even though they'll be more challenging, you won't get confused and you'll be able to solve them okay. If you get caught in not understanding this and how that relates to these, then a more challenging one, you'll be all over the map. Okay, and that's generally what I see. So as long as you have this foundation down, this is the key, in my opinion, is understanding this and the relationship of all these things with that, and you'll be okay. Okay. Let's do some more problems. What is this? This is a problem that doesn't have a, okay. Okay.
Why would you?
Let's call this example 2. That was 1. So what are the concentrations of the
You don't know what they
H
are.
plus and the acetate ion in a solution of 0.1 molar acetic acid? What is the pH of the solution? What is the degree of ionization? And here you're given the Ka. Okay. So last time you got the pH, this time you get the Ka. Ultimately, what must you do first? The equation, because the equation will not be on here, right? Here's the equation. I would just do this as HC2H3O2 double arrow H plus C2H3O2 minus. I would take out the H2O and the H2O from the H3O, but it doesn't matter if you leave it. Okay. You must know this because now you know that you're looking at this thing in a lot of this information. That's the key. Okay. So this I'm starting with 0.10 molar, 0, 0, minus X plus X plus X. And then this is going to be 0.10 minus X plus X plus X. My Ka is this. I can put all that into the equation. I cancel out the minus X since it's so much smaller. And then I solve for X. I solve for X. That gives me the amount of this. And that tells me, then I take that, I put that into the pH equation, negative log. I get the pH. And then I take, of course, that X and X are the same here, so whatever that concentration is, this concentration is, divided by this, times 100, and that's my degree of ionization. Not so bad, right? As long as you know this equation. If you don't know that equation, you're a mess.
The question for the exam is simply we have to memorize the formula for acetate or acetic acid.
For acetic acid, yes, only because it's the polyatomic acetate's common.
Yeah.
Let me, how about this? Does it matter what it is? If I just said HA and clumped that together as A and made that A minus, would it change how you solve this problem? No. Right?
Yeah.
If you don't know, does it really matter what this is? I could just make all that A, so this is just HA. I'll make this A minus, and I'll still solve for it the same exact way, and it won't affect anything as long as I know how this equation fits, right? So you don't have to worry about it. Okay? At least for these types of problems. Nomenclature, obviously, but we're done with that, right? And if you have, what if you had a really big molecule that you didn't know what it was?
Yeah.
But what would be important is knowing how many H's per this thing. That does matter. So if this was H2 this,
That gives it the power.
then you're going to change, some things are going to change over here. You know, the ratios and things could change a little bit. So it could matter, or it'd be polyprotic, and then you would have a double equation. You'd have your first equation is going to go this way. Your second equation will start with this. So this would be, let's say, H2C2H3O2. This would be HC2H3O2 minus. This would then come mixing with water, double arrow, C2H3O2 2 minus, H3O plus, and now you're looking at both H3Os and determining if they're both relevant or not. If this one's probably a lot weaker, and therefore probably won't factor in here, and we could throw in Le Chatelier's principle, shift it the other way, and make up all kinds of stuff to get rid of that X, right? So, but that's where it could, you know, knowing that could matter if there's a second layer. Okay, so just to keep that in mind. Okay, so let's solve this problem. A little bit of time, moving fairly slow, but okay. So here's this, of course. Here's my H chart. Same thing I've already described. That's going to fit into the Ka. Like this, and of course that's much, much smaller, so I can get rid of that. I know the Ka that was given this time, so if I get rid of that, this becomes really easy. It's just this times this and the square root, right? Notice I got rid of that. Gives me this, which gives me that. That's my x. Here, I plug that into here. I solve for my pH. This x is also going to be my x here, so that's my amount here, divided by my amount here, or in this case, if it's 0.1. So 0.1 divided by whatever this x is going to be, that right there, and times 100, and that's my degree ionization. So my pH goes in here, 2.89. Makes sense, it's an acid. And percent ionization is going to be this divided by that, which is going to be 1.3%. See, the other one was 7 point something. This is 7.1. This is 1.3. Different percent ionization, meaning different strengths of the weak acids. And that's what you're seeing here. That kind of cool? So before I used to just say weak acid, about 5% ionization. Now you guys could actually figure out what the actual percent ionization is. How weak or strong of an acid is it? You're now figuring that out as opposed to just hearing me say, oh, it's about 5% dissociation. Because that's all I couldn't tell you all of this in 101, right? Or you'd say, I'd go off on a tangent and you could stare at me like, what's wrong with this guy? What is he talking about? Right? Now it's all put in proper perspective where you can actually figure these things out. So with that, this is a good place to stop. We'll get into mixture of acids, and the only thing I want to say here is the next part, and I'll start on this slide, is we're going to mix two strong acids together to figure out pHs. We'll mix a strong acid with a weak acid, and then we'll mix two weak acids, and we'll try to determine what the pHs are of those. So there we're going to have multiple equations where we have to solve for this in both of them to determine what the overall is, but we're going to use the same procedures we've just done. Okay, so I'll see you Thursday.